Imagine a cast iron pipe that can survive underground for more than a century while carrying millions of liters of water every day. You drive over them, walk past them, and depend on them, yet most people never think about the fiery journey hidden beneath their feet. Inside a pipe factory, raw iron transforms into a perfectly engineered cylinder through heat, centrifugal force, precision machining, and relentless testing. The air smells of hot metal and machine oil, while sparks flash against a backdrop of roaring furnaces. But here's what nobody tells you. A single flaw smaller than a grain of sand can determine whether a pipe lasts 100 years or fails in just a few months. A modern cast iron pipe does not begin as a pipe at all. It begins as a carefully balanced recipe of iron ore, recycled scrap metal, coke, limestone, and small amounts of alloying elements. Each ingredient changes the final strength, flexibility, and corrosion resistance of the pipe. Think about this. Manufacturers can melt more than 100 tons of metal in a single furnace batch, and every percentage point in the chemistry matters. What happens next surprised even experienced engineers, because the molten iron must be controlled with extraordinary precision before it can become a pipe. The journey often starts in iron ore mines in countries such as Australia, Brazil, India, and South Africa. The ore may contain 55 to 68% iron, and miners crush, wash, and concentrate before shipping it to steel and foundry industries around the world. Large factories also rely heavily on recycled scrap metal, which can make up 30 to 50% of the charge in some furnaces. This recycling reduces the need for new ore and lowers energy consumption, compared with producing iron entirely from raw ore. But the supply chain is still enormous, with raw materials traveling thousands of kilometers by truck, rail, and cargo ship before reaching the pipe plant. At the factory, workers blend iron ore, scrap metal, coke, and limestone in carefully measured proportions. Coke provides the carbon and heat needed for smelting, while limestone helps remove impurities by forming slag. A typical melt charge may weigh between 20 and 100 tons, depending on the size of the furnace and the production schedule. The goal is not just to melt metal. It is to create molten iron with the right carbon and silicon content for strong, durable pipe. And this is where it gets truly extraordinary, because even a small chemical imbalance can create brittleness or weaken the pipe wall. Before melting begins, laboratories test the raw materials for carbon, sulfur, phosphorus, and silicon content. Sulfur and phosphorus must remain very low because they can make the iron brittle and reduce impact resistance. Many modern pipe manufacturers target sulfur levels below 0.02% and phosphorus below 0.08%. Samples travel from the receiving area to spectrometers that can analyze the chemical composition in seconds. Most people never think about this hidden laboratory work, yet it forms the first quality gate that determines whether the final pipe can withstand decades of underground pressure. The environmental impact of cast iron pipe production remains a major challenge for the industry. Mining disturbs land. Furnace operations consume large amount of energy, and carbon dioxide emissions come from both fuel combustion and chemical reactions. However, the long service life of cast iron and ductile iron pipes can offset some of that impact because the pipes often last 75 to 100 years or more. Recycled scrap metal also reduces the demand for newly mined iron ore. But here's the cliffhanger. Once the raw materials enter the furnace, the metal reaches temperatures hotter than molten lava, and the real transformation begins. Ns. Inside the melting furnace, the charge heats to approximately 1,400 to 1,500 degrees Celsius, or 2,550 to 2,730 degrees Fahrenheit. The furnace roars with deep, continuous sound as burners or electric power raise the metal above its melting point. Slag floats to the surface, and workers remove it to improve the purity of the molten iron. The liquid metal glows bright orange and white, and the air shimmers from the intense heat. What happens next surprised even experienced engineers, because the molten iron must be treated with magnesium to create ductile iron, a stronger and more flexible form of cast iron. During magnesium treatment, small amounts of magnesium alloy enter the molten iron and change the shape of graphite from flakes into tiny nodules. This transformation greatly improves tensile strength, impact resistance, and ductility. The treatment usually occurs in a covered ladle because the reaction can be violent, producing sparks and bursts of smoke. Operators monitor the temperature and chemistry carefully, often aiming for a pouring temperature around 1,350 to 1,450 degrees Celsius. And this is where it gets truly extraordinary. A microscopic change in graphite structure determines whether the pipe can flex under ground movement instead of cracking. The treated molten iron then moves to the centrifugal casting machine. A cylindrical mold spins at speeds that can range from about 300 to 1,200 revolutions per minute, depending on the pipe diameter. Workers pour the molten iron into the rotating mold, and centrifugal force pushes the metal outward against the mold wall. This creates a dense, uniform pipe wall with fewer internal voids than many other casting methods. The sound resembles a powerful turbine, and the glowing metal forms a perfect hollow cylinder in just a few minutes. After casting, the pipe cools in a controlled manner to prevent internal stresses and cracking. Cooling may take from several minutes to over an hour, depending on pipe size and wall thickness. Some manufacturers then heat treat the pipe to refine the microstructure and improve mechanical properties. During annealing, temperatures may range from about 850 to 950 degrees Celsius, followed by controlled cooling. But here's what nobody tells you. Cooling too quickly can create hidden stresses that may not appear until the pipe is buried underground and subjected to pressure. Once the pipe cools, machining stations trim the ends and create the socket or spigot profiles needed for pipe joints. CNC machines cut the pipe ends with tolerances often measured in fractions of a millimeter. The machines produce a sharp metallic sound as cutting tools remove excess material and create smooth sealing surfaces. Operators check dimensions continuously because a poorly machined joint can cause leaks in a water distribution system. And this is where the process becomes even more demanding because the pipe still needs protective coatings and rigorous testing before it can leave the factory. Modern cast iron pipe plants rely heavily on automation to maintain consistency. Robotic arms handle hot pipes, automated conveyors move them between stations, and sensors track temperature, speed, and position in real time. AI-assisted vision systems can detect surface defects such as cracks, pits, or irregular coatings. Laser scanners measure pipe diameter and wall thickness with tolerances that may be as tight as plus or minus 1 millimeter, depending on the specification. Most people never think about this invisible digital layer, yet it helps factories produce thousands of pipes with remarkably consistent dimensions. Quality control begins with visual inspection, but it quickly moves into advanced non-destructive testing. Ultrasonic testing sends sound waves through the pipe wall to detect internal voids, inclusions, or cracks. Hydrostatic pressure testing fills the pipe with water and subjects it to pressures that may exceed 50 bar, or about 725 psi, depending on the pipe class. If the pipe leaks, deforms, or fails to hold pressure, inspectors reject it immediately. What happens next surprised even experienced engineers, because rejection rates in high-quality plants may remain below 2% thanks to continuous monitoring. The inside of the pipe usually receives a cement mortar lining, while the outside often receives a zinc coating and bituminous or epoxy topcoat. The cement lining protects water quality and reduces internal corrosion. Zinc coating acts as a sacrificial layer, helping the pipe resist external corrosion in soil environments. Coating systems must meet strict thickness and adhesion requirements, often verified with electronic gauges. And this is where it gets truly extraordinary. A pipe that appears simple on the outside actually carries multiple engineered layers designed to protect it for decades underground. International standards such as ISO 2531, EN 545, and AWWAC 151 define the mechanical and dimensional requirements for ductile iron pipes. Manufacturers test tensile strength, elongation, impact resistance, hardness, and coating performance. Sample pipes may undergo bending tests, crushing tests, and repeated pressure cycles to simulate decades of service. Despite all the automation, skilled metallurgists and inspectors still play a critical role in interpreting unusual test results. But here's the cliffhanger. Even after passing every factory test, the pipe's true value only becomes clear when millions of people rely on it every day. The global ductile iron pipe market produces several million metric tons of pipe each year, with estimates commonly exceeding 6 million metric tons annually. The market value runs into tens of billions of US dollars because these pipes support municipal water systems, wastewater networks, and industrial infrastructure. China leads global production, followed by countries such as India, the United States, Turkey, and several European manufacturers. Together, these regions supply a large share of the world's water distribution projects. Think about this. If the pipes produced in a single year were laid end to end, they could stretch around the earth many times. Cast iron pipe manufacturing has evolved dramatically over the last 50 years. Traditional gray cast iron pipes, which contain flake graphite, gradually gave way to ductile iron pipes with nodular graphite because they offer higher strength and better flexibility. Modern centrifugal casting, automated chemistry control, and advanced coatings have improved reliability while reducing defects. The industry also employs hundreds of thousands of workers worldwide across mining, recycling, foundries, coating plants, logistics, and installation. And this is where it gets truly extraordinary. A technology first developed in the 19th century continues to evolve with robotics, AI inspection, and smarter corrosion protection. Did you know that some cast iron water mains installed more than 100 years ago still remain in service today? Did you know that ductile iron pipes can achieve tensile strengths exceeding 420 megapascals while still maintaining useful flexibility? And did you know that the cement lining inside many pipes helps maintain water quality by reducing internal corrosion and surface roughness? These facts reveal why municipalities continue to choose cast iron and ductile iron pipes for critical infrastructure. But here's what nobody tells you. The future of pipe manufacturing may include even smarter sensors embedded in water networks to monitor pressure, leaks, and corrosion in real time. From iron or deep in the earth to a finished pipe buried beneath a city street, the journey of a cast iron pipe combines geology, metallurgy, precision engineering, and relentless quality control. Every stage depends on exact chemistry, extreme heat, controlled cooling, accurate machining, and protective coatings. Most people will never see the roaring furnace, the spinning mold, or the pressure test that proves the pipe can survive decades of service. Yet every time clean water flows from a tap, this hidden manufacturing chain plays a quiet role in daily life.